In this video, we're going to look at Hund's rules for determining what the ordering of energy is for a given set of term symbols for a certain electronic configuration. So Hund's rules tell us what to do when we have a number of term symbols for a given electronic configuration. So in order to rank the energies, or the relative energies of these term symbols, we just follow these rules and we should be able to determine an order for which is lowest in energy, then which is next lowest, etc., in order to be able to see which one is the ground state of a given configuration. So these rules are, first you look at S, the spin angular momentum. The largest S is the most stable state. If there are multiple states with the same S, multiple term symbols with the same S, then the one with the largest value of L, the largest orbital angular momentum, is the most stable among states with the same value of S. Among states that have the same value of S and L but differ in their value of J, there's one little caveat here. If your subshell is less than half full, so for example in a P subshell this would be P1 and P2, and if your subshell is greater than half full, for a P this would be P4, P5. For D this would be D6, D7, D8, D9, etc. So if you're less than half full, then the smallest value of J is the most stable term symbol. And if you're greater than half full, like D9, then your largest value of J is going to be the most stable, given that you have the same value of S and L. Okay, so using these rules, let's look at the two examples that we did in the previous videos and rank the energy of those term symbols. So for a carbon atom in its ground state, so we have carbon atom ground state was 1s2, 2s2, 2p2. So that gave rise to the following set of term symbols. We had singlet D2, triplet P2, triplet P1, triplet P0, and singlet S0. Okay, so let's look at all of these here, and we're going to rank them in order of their energy. So first, what the largest S. So we have singlets and we have triplets. The triplets have S equals 1, the singlets have S equals 0. The triplets are more stable. So our triplets are all triplet P's, so our ground state is going to be a triplet P. Alright, so given that we have a triplet P, then the largest L is going to be most stable. All three of these triplets are P's, so that doesn't help. Then third, we go to, if we have the same S and L, if the subshell is less than half full, carbon is 2p2 in its only partially filled subshell. That's less than half full. There are 6 possible spin orbitals in a p subshell, so it is less than half full. So that means the smallest value of J is going to be the most stable. So in our case, that is J equals 0. So our ground state is going to be the triplet P0. Then we have triplet P1, triplet P2, less than the energy. So the lowest energy is the triplet P0. Then we go back to the top. We have our singlet D and singlet S left. They are both singlets. They have the same S. So we look at L. D has a larger value of L. L equals 2. So the singlet D2 is more stable than S, which is our highest energy term there, singlet S0. Okay, so that is our relative order of those 5 term symbols, our relative order in energy. So for a carbon atom, carbon has a triplet P0 ground state. This means that the lowest energy state of a carbon atom is going to be a triplet P0 term symbol. Okay, then let's also look at the other example we did, which was, we could say something that had a 3D9 configuration and all of the other subshells were full. What would be a copper atom if copper wasn't an exception and had 4s1 3d10, but let's pretend for a moment that there's some hypothetical atom with a 3d9 configuration at its valence. Okay, so for that we determined that the two term symbols we have are going to be doublet D 5 halves and doublet D 3 halves. Okay, so in each of these cases, they are both doublets. They have the same value of S. They are both D. They have the same value of L. L equals 2, and S equaled 1/2. So is this subshell more or less than half full? D holds 10 electrons in its 10 spin orbitals, 5 spatial orbitals. And 9 is obviously more than half of 10, so our subshell is greater than half full, so our largest value of J is going to be most stable. So our ground state for this hypothetical atom is going to be the largest value of J. So our doublet D 5 halves is more stable than doublet D 3 halves, and our ground state is in fact of this hypothetical atom is the doublet D 5 halves term symbol.